All right, we know now how to find the angle if we are aware of the value of its sine, its cosine, or its tangent. We use simply the inverse sine, the inverse cosine, or the inverse tangent function on our calculator, and we get a very accurate approximation. Well, what if we knew instead the sides of the triangle? What would we do then? Well, the answer is it really isn't much harder. It just has one extra step. Suppose I want to be able to compute these angles theta and alpha in this triangle here. Well, I could start with this observation. If I look at the angle theta, I know that its sine is the length of the opposite side divided by the length of the hypotenuse. So sine of theta is 2 divided by the square root of 13. Then I do just exactly what I did up here in the earlier examples. I take the inverse sine of the sine value on my calculator, and that turns out to be 33.69. It looks like this. Take the inverse sine of 2 divided by the square root of 13, and I come up with about 33.69 degrees. Now, if I wanted to compute alpha, I actually have a couple of options here. Option number one, I could do it simply by subtraction. I know that the sum of the measures of all the angles in the triangle is 180 degrees. There's a 90-degree angle in there. I've computed the value of theta, at least approximately, and I could subtract those off from 180, leaving 56.31 degrees. As another option, I could work with a trig function directly. The angle alpha, well, we could read off its sine, its cosine, 2 divided by root 13, and its tangent, 3 divided by 2. So why don't we take the third option there? Tangent of alpha is equal to 3 divided by 2, or 1.5. The angle alpha must be the tangent, the inverse tangent of 1.5, which our calculator tells us is 56.31. And we do that, of course, just as we have in the previous examples, 56.31 degrees approximately. So there's what to do if you're given the sides of a triangle rather than the values of the trig functions directly.